I have a report now that they are sending a new rover to Mars, and we are responsible for doing one thing, which is programming the algorithm inside the rover which checks if numbers are prime. Because let's say our rover is communicating using RSA, it needs an algorithm inside that can do a primality test. Now, when you design a rover or anything to go into space, you have to be very efficient in every way. So the components used have to be very light. The amount of power every subsystem uses has to be minimal. You have to be saving energy and mass at every point in the design process. So we have our work cut out for us because we have to be able to deal with numbers up to this size, and it has to do it very fast. So if we give it a very small input, let's say just 90, it should be able to calculate that almost as fast as this entire number. So as the input grows, we don't want to see any of this noticeable slowdown. Now, I want to analyze the user questions or the ideas users have had, which were really good from a mathematical standpoint. We are checking if n is prime or composite. So given some number n, think of the space of all possible n's as, say, if n is 100, then this space is 2 to 100. And what our algorithm is doing is it's searching this space. Okay, so you can think of algorithms as searching a space. And at each point, it's asking, think of it as a step, right? A primitive step. It's asking a question. And it's actually a composite test, the question. So say this is we're at number A. We would say in the trial division method is n divided by A. We just try this. We drop A here and we try if n divides A. And we see if the remainder is 0, which means A is a divisor of n. Then we can say, we know 100% we raised the flag. We're 100% sure it's composite. Otherwise, at each step, we aren't quite sure. It might be prime, but we're not sure. So we continue searching until we hit the end. And remember, our wall in this case was at the square root of n. That's at the worst case situation occurs when n's prime. We search all the way to the square root of n, and then we can say, it is prime, and we're 100% sure. So in the case where n is even a multiple of 2 prime, so 7 times 7 equals 49, if we throw 49 into our algorithm, it is the worst case occurs. We go all the way until the square root of n. So the first set of questions from, for example, the fourth dimension asks, once we rule out 2 as not divisible, then all multiple of 2 could be ruled out. The same for 3, 4, 5, etc. So that's a really great point. Our old algorithm was stepping along one at a time, but we could be using patterns we know about composite numbers, such as we know for sure that if a number is divisible by 2, then it's composite, if it's greater than 2, so 2 is prime. But then we can say, 4 is composite, 2, I missed 5 here. Sorry about that. 4, 6, 8, 10. And instead, we can take this step like this. 3, 5, 7, 9. So one category of questions, they all try to reduce this space. So if we eliminate all the even numbers, now the check space, instead of being up to the square root of n, is the square root of n divided by 2. And we can find other patterns in composite numbers to try to make this even smaller. The other type of question concerns the case where we find a composite witness. That is, we find an A that allows us to say, we know n is composite. Lola said, wouldn't leaving the loop as soon as we find prime check equals false cut down on some of the time? And yes, that's totally correct, and it's something we want to do. As soon as we are searching along using some step defined by whatever pattern we're using, we find a composite witness. That means it passes our test and we say 100% composite. We should halt early. We stop and say, we're done. We won't continue searching. And this halting early is great, except it doesn't help us in the worst case. which is if n is prime, then the early halting won't help us. And now we can visualize how these improvements allow us to reduce the space, thus preventing as many checks happening inside the computer, which depending on our computer will reduce the amount of time it takes. So now I can show you the visualization I've set up below, which allows us to compare two algorithms based on how many steps occur during their execution. On the left is algorithm A, which is trial division, which checks from 2 to the square root of n, and on the right is algorithm B, which is, let's just say, our improved algorithm. And in this case, I've applied the check if it's divisible by 2, so we only do half as many steps. And I also terminate early in this algorithm B. So it's not perfect. I've just applied a few user modifications so we can see what happens. And now I'm going to just play with this to show you it. Here we can see, as I scroll, we see algorithm A. We have the output, whether it's composite or prime. And at the bottom, you'll see the number of steps. So the first thing to notice is on the right-hand side, every other number takes only one step. And we know why that is, because if it's an even number, such as this, it will quit. So our old algorithm took 314 steps, and our new algorithm only took one step because it checked if it was divisible by 2. So that seems like a really nice optimization. However, as we build our input, you'll notice the steps increase, and the bar grows and turns red once we hit the region, once we approach the region where we're going to crash. So this red line up here is step limit. If your bar hits there, we fail, which means our rover would break. And in this case, the browser will actually crash. So I'll try to get close to it. So I'm close to it now, and it's running very slow. I can feel that my browser is just about to crash and give me the circle of death. But notice our improved algorithm took only 2 steps in that case. But remember the worst case. So I have a few large prime numbers saved here, for example. We have to be able to handle any case. We don't know what we're throwing at our algorithm. So if I throw a large prime at it, look what happens. Algorithm B, as we know, is taking half as many steps in the worst case, but it's still taking many steps here because it's the worst case, right? So we're getting close to crashing here, and this is not a very long prime. We're still way under 15 digits. And when I put this 12, I think this is a 12-digit prime into our algorithm, let's see what happens. It's lagging. Maybe it's going to crash. Look what happened. Both algorithms went way overboard. So it didn't work. Our improved algorithm is not good enough yet. But now we have an understanding of what we're trying to improve, which is number of steps in the worst case. And we also have this cool tool which allows us to visualize how fast it's growing, how fast the number of steps grows as our input grows. And below, I'll explain how I set this up so you can set up your algorithm and compare it with the base case and see how much better you can do.